magnetic circuits. This is the last webinar in this series. In today's webinar, we would be discussing about the fundamentals of magnetic circuits. Now, as we have been doing in other webinars, the today webinar will also start with the ebook, which is the fundamental part of our e-learning environment on electrical machines. Actually, in this book, the discussion on magnetic circuit starts from chapter 2. In this chapter, we will be going through the fundamentals and basics of the magnetic circuit, and we will learn how these magnetic circuits are actually analyzed and what are the basic equations and fundamentals that are used to analyze the magnetic circuits. We will also see some other characteristics of magnetic circuits such as the BH curves and the hysteresis and eddy current losses. So let's just start with the magnetic circuits. Now the study of magnetic circuits is very important for electrical machines because the ferromagnetic cores of the electrical machines are actually nothing but magnetic circuits. Actually, the entire electrical machines are magnetic circuits, and the machines work on the principle of conversion of electrical energy into mechanical energy via the magnetic circuit. So the machines, be it transformers or be it motors, they utilize the magnetic circuits in a very big way. To analyze the magnetic circuits, actually it is possible to have a very detailed analysis of magnetic circuits using finite element methods or boundary element methods or various other numerical techniques. All these numerical techniques give very good and very accurate results of the magnetic circuits. However, in today's webinar, to understand the fundamentals of magnetic circuits, we will try to build up some very simple models, some very simple mathematical models which can be used to analyze the magnetic circuits. Now, one thing we have to keep in mind, the results that will be obtained through these simplified models might not be very accurate when compared to the experimental results, but then they give a very deep insight into the functioning and the working of the magnetic circuits. So here in today's webinar, we will be focusing on those simple mathematical models of the magnetic circuit. Now the analysis of magnetic circuits actually starts from two very fundamental equations. These are the Maxwell's equations. So we'll be utilizing two of the four Maxwell's equations, and they are listed in equation 2.1 and 2.2. Now out of these two equations, equation 2.2 is very important. This equation states that magnetic monopoles do not exist. Now this is a very important thing because if we look carefully, we do not have electrical machines, the rotating electrical machines with 3, 5, 7 or 9 poles. The machines are always with even number of poles. So an electrical motor might have 2 poles, 4 poles, 6 poles, 8 poles, but it can never have 3 poles or 5 poles because magnetic monopoles do not exist as governed by this equation 2.2. So this is a very fundamental thing which we have to keep in mind. Now to build up our model of the magnetic circuit, we will have to make some simplifying assumptions, and one of the assumptions that we make is that we do not take into account saturation. We do not take into account magnetic saturation. Now once we do not consider magnetic saturation, then our analysis becomes simpler. Moreover, another important assumption that we are going to make is that we consider a constant permeability for the ferromagnetic materials. Okay, because most of the magnetic circuits that we are going to analyze in today's webinar are made up of ferromagnetic material. Okay, now this assumption of having a constant permeability makes the magnetic circuits linear, and once we have linear circuits, then obviously the analysis becomes simpler. So here in figure 2.1 we see a very basic fundamental magnetic circuit. Now if we look at this figure very carefully, then we can see that we have a ferromagnetic core, okay, which is represented in blue color, and this core has a permeability mu. Now on one of the arm of the coil, one of the arm of the core, a coil is wrapped around it. Okay, this coil has certain number of turns. In this figure we have shown just 3 turns, and at the terminals of the core of the coil we have a voltage source or an EMF source. Okay, now once we apply voltage across the terminals of the coil, a current starts to flow through the coil. Now as the current starts to flow through the coil, it creates something known as magnetomotive force, or the MMF in short. MMF stands for magnetomotive force. Now this magnetomotive force results in flux to be formed inside the ferromagnetic core, and the path of the flux lines is shown here in this figure through the dotted lines. So these dotted lines show the flux which is present inside the ferromagnetic core, and the direction of the flux lines can be determined from the right hand thumb rule. Okay, so if we apply right hand thumb rule to this figure, we can see that the direction of the flux lines is clockwise as shown here. Okay, now one of the major assumptions that we have made here is that the permeability of the ferromagnetic core is very high. Now this very high permeability of the ferromagnetic core ensures that all the flux lines are confined within the material and they do not leak out into the surrounding air. Now this makes the analysis simpler. So it's something which we have to keep in mind. Throughout the analysis we would assume very high permeability of the ferromagnetic core so that the leakage flux is not present and all the flux lines are confined within the ferromagnetic core. Now to understand the magnetic circuits, it is important to look at some of the fundamental terms, and one of the fundamental electromagnetic quantity is MMF, or the magnetomotive force. Now this magnetomotive force, as we have seen earlier in this today's webinar, it is equal to number of turns in the coil into the current flowing through the coil. Okay, so if we have a coil which has say 10 turns and 2 ampere current flows through it, then the MMF created by this coil is 10 into 2, which is 20. Okay, and the SI unit for the MMF is ampere turns. So in our example which we have considered, where the coil had 10 turns and 2 ampere current passes through that coil, then the MMF is equal to 20 ampere turns. Now this MMF is the source or the cause for the flux to flow in the ferromagnetic core. Now another important electromagnetic quantity that we are interested in is the magnetic field intensity. The magnetic field intensity is very closely related to the MMF, and it is given by expression 2.4, where magnetic field intensity is equal to MMF by L. Now this L is the path taken by the flux lines in our magnetic circuit, and we have to ensure that the flux lines close a path. Okay, we can't have an open path. The flux lines should close a path. Okay, if we look at this figure here, the flux lines, they are closing a path. Clear? So the L is the total length traveled by these flux lines. Clear? So it is this L which is used in expression 2.4, and the SI unit for magnetic field intensity is ampere turn per meter. The other quantity that we often use in the analysis of magnetic circuits is the flux density. Okay, so this flux density is defined as the concentration of flux in a particular section of magnetic circuit, and it is defined as shown in equation 2.5. Flux density is equal to flux per unit area, and its SI units is Webers per meter square or Tesla. So these are the two SI units for flux density, and Tesla is the most commonly used unit for flux density. Apart from flux density, we have one more important parameter for the magnetic circuits, and it is known as permeability. And permeability is defined as the ratio of flux density to magnetic field intensity, or mu is equal to B by H as shown in equation 2.6. Now permeability in principle is a measure of the ease with which the flux lines can flow through a material. That means if a material has a high permeability, then flux lines can flow through it easily. If the material has a low permeability, then the flux lines find it difficult to flow through it. So permeability, usually defined as mu, is the ease through which the flux lines can pass through the material, and the SI unit for the permeability is Weber per ampere turn meter. So this is the SI unit for permeability. Now apart from permeability, one of the most frequently encountered quantity in magnetic circuits is reluctance. Okay, so reluctance, as the name suggests, it is the opposition that a material poses to flow of flux lines. Okay, so if a material has a very high reluctance, it means flux lines will find it very difficult to pass through it. On the other hand, if a material has a very low reluctance, then the flux lines find it very easy to pass through it. Now one thing we have to keep in mind, the cores that are used in electrical machines, be it transformer or be it rotating machines, they are made up of material which have very low reluctance, because we want that most of the flux, or if possible the entire flux, should flow through the ferromagnetic core, because it is through this ferromagnetic core that the conversion of electrical energy into mechanical energy takes place. So this principle of conversion of electrical energy into mechanical energy has already been discussed in our previous webinars. And here throughout the book we have multiple solved examples. Every chapter has number of solved examples, and these solved examples, they actually help the student to understand the principles and the theories that have been discussed. So usually if we click here, we can expand the example and one can see the detailed solution of the example. So we will not go to the example right now, but we will continue with our discussion. Usually, while analyzing the magnetic circuits, instead of using permeability, we use another quantity which is known as the relative permeability. Relative permeability actually is the ratio between the permeability of the material and the permeability of free space. Now one thing we have to keep in mind, since relative permeability is a ratio of two permeabilities, it does not have any units. Okay, it's a unitless quantity, and this is very commonly used in the analysis of magnetic circuits. Now after having gone through some of the fundamental electromagnetic quantities, we now try to draw an analogy between the electric and the magnetic circuit. So if you look very carefully, the magnetic circuits are not very different from the electric circuit in terms of their treatment. Just like in case of an electric circuit, whenever we apply a voltage, a current flows through the circuit, and the current flowing through the circuit is given by Ohm's law, and it's shown here in the second part of equation 2.8. So the current through the circuit is equal to applied voltage or the EMF, electromotive force, divided by the resistance of the circuit. Now similarly, in case of magnetic circuits, whenever we apply an MMF, flux is set up inside the magnetic circuit or the ferromagnetic core, and this flux is given by something very similar to the Ohm's law of the electrical circuit. The flux is equal to MMF divided by the reluctance, as shown in the first part of the equation 2.8. Now if we look at these two equations, we can see that flux is analogous to current, MMF is analogous to EMF, and the reluctance is analogous to resistance. Now this is a very important analogy, because with this we can establish that the treatment of the magnetic circuits is very similar to that of the electrical circuit. And this can be seen here. For example, in case there are multiple number of reluctances connected in series, let's say there are n reluctances connected in series, then the net resultant that we have is equal to sum of those individual reluctances, as shown here in equation 2.9. So the resultant of the reluctances connected in series is the sum of the individual reluctances. Similarly, if we have n reluctances connected in parallel, then the resultant reluctance is given by equation 2.10. Now if we look at equation 2.9 and 2.10 carefully, then we would find that this is exactly the same expression that we have for n resistances connected in series or n resistances connected in parallel. Now this was possible because we have seen earlier that the magnetic circuits are analogous to electrical circuit. Now again here we encounter a problem. This exercise actually helps the student to understand the relation between the various electromagnetic quantities that we have seen earlier, and we will not go into the details of this example here, but we will continue with our discussion. Now here, in case of magnetic circuits, we also use one more very fundamental relation, and this relation is between the flux density and the magnetic field intensity. Now for a free space or vacuum, okay, the magnetic flux density is equal to the magnetic flux density is equal to the permeability of the free space multiplied by the magnetic field intensity. That is, B is equal to mu 0 H, as shown here in equation 2.11. So this equation is for free space. Now if we consider any other material, okay, be it a ferromagnetic material, diamagnet material, paramagnet material, hard ferromagnetic material, then the relation between the magnetic field intensity and the flux density is given by equation 2.12. And here again this equation states that the flux density is equal to permeability of the material mu into the magnetic field intensity H, where mu we can also write it as mu 0 into relative permeability of the material mu r. Okay, so this is about the relation between the magnetic field density and the magnetic flux intensity. Now based on this value of mu, we can classify material into various types. We have paramagnetic material, diamagnetic material, ferromagnetic material, and so on. However, we will now focus our attention to one of the very fundamental properties of ferromagnetic material. Now we are focusing mostly on ferromagnetic material because the cores of the electrical machines is made up of ferromagnetic material. Either we consider the transformer or the motor, it does not matter. The core is invariably made up of ferromagnetic material. And to characterize the ferromagnetic material, that means to find out which kind of ferromagnetic material is best suited for a given machine, can be done by studying the BH curve or the magnetization curve of the ferromagnetic material. Okay. Now to understand this magnetizing curve or the BH curve, we will have a look at the animation. So in this animation, we will try to explain the BH curve. So here we show a magnetizing fixture. Okay, it has large number of turns made up of copper, and this copper coil is connected to a current source. Now here we see that a test material has gone inside our measurement fixture. Now in this measurement fixture, if we see that in case there is no external magnetic field present, then what happens is that every material has its internal magnetic field due to the spin of the electrons. Clear? So we call them as grains. Now these grains are randomly distributed in a material which has not been magnetized earlier. Now due to this random distribution of the grains, the resultant magnetic field inside the material is zero. Okay, so the material does not show any magnetic behavior. But as soon as we start to apply some external magnetic field, these grains, they start to orient themselves in the direction of the applied magnetic field. So you see here we have a north pole here and all south pole in this place, in this location. We see that these grains are now starting to orient themselves in the direction of the applied magnetic field. Now as we keep on increasing the applied magnetic field, more and more grains, they start to orient themselves in the direction of the applied magnetic field. But then there comes a point where all the grains are almost oriented in the direction of the applied magnetic field, and increasing H or the applied magnetic field does not result in drastic increase in the alignment of the grains, because most of them, almost 99% of the grains, are aligned in the direction of the applied field. Now once a material reaches this position where majority of the grains are aligned in the direction of the applied magnetic field, then it is said to be in saturation. So the condition which is shown here on the screen is the condition of saturation. The material is saturated. It means if we keep on increasing H, B will increase very slowly, and once that happens, we say that the material starts to behave like air or free space. Okay, so that was a simple explanation of the BH curve. Now the detailed explanations of it are given in our ebook, so all the users of this ebook will find the detailed explanation of the BH curve. Due to shortage of time for this webinar, we are not going into the details of the BH curve, and our users of the book can easily find that inside our material. Okay, here in this figure we show a typical BH curve of a material. Okay, so if we buy some ferromagnetic material, then the manufacturers usually supply the BH curve for that material, and a sample BH curve is shown here in figure 2.7. Now apart from the BH curve, the materials also exhibit something which is known as hysteresis. Okay, so now hysteresis is a very important and an interesting phenomenon, and this figure here, figure 2.8, tries to explain the hysteresis phenomenon. Now to understand the hysteresis, let's consider a material which was at rest. At rest means it is not magnetized. That means all the domains are randomly oriented, and if we take the vector sum of all those domains, then we do get zero magnetization inside the material. Now if we start to apply a positive magnetic field intensity, then we see that initially the material follows the path shown here in the red path. Okay, the first part of the figure 2.8. Then if we start to decrease the magnetic field intensity, then the material does not retrace the red path which was shown earlier, but it takes some other path. Okay, now this actually can be shown better in this animation. So let's have a look at the animation of the hysteresis. So we see here, initially our material was randomly oriented, and we start to apply an external magnetic field, and the grains, they start to orient themselves in the direction of the applied magnetic field. Then there comes a point where most of the grains are almost aligned, which is the point shown over here. Clear? And now if I start to reduce the applied magnetic field, then what happens is that my material does not trace the path from A to B that it had taken initially, but starts to take some other path. And this can be shown here in the figure on the right corner of the screen, right top corner. You see the dot. Okay, this dot shows that which path my material is taking. So due to this path, what happens is that there comes a point when the applied external magnetic field is 0, but some of the grains, they still remain oriented in the direction in which the magnetic field was present. Okay, now if you see here in this animation, we can see that the applied external magnetic field is 0. There is nothing present here, no external field, but the grains are still oriented in one direction. Okay, so this results in some residual magnetism. Now what happens is, if we start to apply a magnetic field in the opposite direction, then there comes a point, okay, where all the grains inside the material are randomly oriented, but we do still have an applied magnetic field. So it means that even in the presence of applied external magnetic field, the grains inside the material are randomly oriented, and its flux density is equal to 0. And this point is known as coercive force. Now if we keep on increasing the applied magnetic field further, then we would see that all the grains of the material are then aligned in the direction of the applied magnetic field. So since the applied magnetic field is in the opposite direction to the previous case, we see that the grains are aligned in the opposite direction. And then again, once we start to decrease the applied magnetic field, and there would come a point where the applied field is 0, but then there are still some grains which are oriented in a specific direction, and the material has some residual magnetism. Okay, and then this process continues. So if we keep on increasing and decreasing the magnetic field, then the material will keep on traveling on the hysteresis loop, and this process continues. So this is about the hysteresis loop. Now one consequence of the hysteresis loop is that it creates losses. Okay, and these losses form one part of the core losses. We have read already in our electrical machines, we have core losses, and there are two types of core losses: the hysteresis losses and the eddy current losses. Now let's have a look at the hysteresis losses. So the previous hysteresis loop, okay, which is shown here in figure 2.9, this loop is divided into two separate halves. Now to calculate the hysteresis losses, actually we use expression 2.16. The expression 2.16 tells us that the energy, okay, the energy supplied by the source to a ferromagnetic material is equal to magnetic field intensity into the rate of change of magnetic flux density. Okay, now let's look at the equation 2.16 and look at the figure 2.10. Now in figure 2.10, if we move from point A to point B, then we can see that the magnetic field intensity H is positive, whereas the magnetic flux density, okay, the rate with which the magnetic flux density decreases is negative. So if we go from point A to point B, the magnetic flux density has a negative slope. So from equation 2.16 we can see that H dot dB is going to be a negative value. So it means the energy is negative. Negative energy means that the material is feeding back its stored energy into the source. If now we consider that we move from B to C, okay, then here we can see that the magnetic field intensity H is negative, and the slope of the curve from B to C is also negative. So from equation 2.16 we get that the energy is positive. So positive energy means that the source supplies energy to the material. Similarly, if we go from C to D, again the value of H is negative and the slope of the curve while going from C to D is also negative. So our energy is positive from equation 2.16, and it means that the source is supplying energy to the material. However, if we go from point D to point E, here we can see that H is negative, but the slope of the curve while traveling from D to E is positive. So equation 2.16 gives that the energy becomes negative. So negative energy means the stored energy inside the material is fed back to the source. And then if we go from E to F and finally from F to A, we can see that the energy is supplied by the source to the material. Now if we look at the complete curve, okay, the complete curve which starts from A then to B, C, D, E, F, okay, so if we look at the complete curve, then we see that the energy supplied by the source, shown in green color, is greater than the energy that the material returns to the source, shown in blue color. So in totality, the material absorbs energy from the source. Now this absorbed energy from the source is eventually dissipated as heat, okay, and this is known as hysteresis loss. This hysteresis loss can be calculated using the expression shown in equation 2.17. So this is an empirical relation to find out the hysteresis loss. The details are given inside the book, so due to shortage of time we will not be going into great details about the explanation of this equation on hysteresis losses. However, we should keep one point in mind. Hysteresis is not always undesirable, especially if we want to create magnets, permanent magnets. Then we desire hysteresis, and we desire to have a material which has a very wide hysteresis loop. So those kinds of materials are known as hard ferromagnetic material. So let's see how the hysteresis loop of a hard ferromagnetic material look like. So here in this animation we can see the hysteresis loop of a hard ferromagnetic material. Now let's see what happens. Once we magnetize the material completely and then start to reduce our external magnetic field H, then there comes a point when the applied magnetic field is 0, but most of the internal domains remain aligned in the direction in which the field was present. Okay, so if you see here this figure carefully, my applied external magnetic field is 0, but even in the absence of applied external magnetic field, most of my domains remain aligned in the direction in which the field was present. So this material has a very high residual magnetism, and it starts to behave like a strong permanent magnet. Okay, so this is the reason why I said that sometimes it is desirable to have a very wide hysteresis loop. However, we have to keep some point in mind. If we are planning to design a core for our electrical machine, a transformer or a motor, doesn't matter, the core should be made up of a material which has a very narrow hysteresis loop. And if we are planning to make permanent magnets, then it should be made up of a material which has a wide hysteresis loop. So this is what we have seen in the animation. We saw the animation of a soft ferromagnetic material with a thin hysteresis loop and of a hard ferromagnetic material with a thick hysteresis loop. Now, apart from the hysteresis, we have one more loss which is known as the eddy current loss. The eddy current losses can be calculated empirically using the expression 2.18. However, the formation of eddy current losses is something which is very important to understand. And to understand how eddy current losses are produced, let's have a look at this animation. So in this animation we see that there is a green material which is a ferromagnetic material, and it is exposed to an alternating magnetic field. So this alternating magnetic field is created due to the alternating current which flows in our machines and transformers and all electromechanical energy conversion devices. So you see during the positive half the orientation of the north and the south pole. Once the current enters the negative half, we see that the orientation of the north and the south pole is flipped. So in case of a machine, the ferromagnetic material is exposed to such kind of a magnetic field which increases and then decreases and then goes into the negative region and increases and then decreases. So the alternating current flowing through the coils of the ferromagnetic material results in an alternating magnetic field. Now, due to this alternating magnetic field, a current starts to develop inside the ferromagnetic core. The ferromagnetic core has certain resistivity, and due to that resistivity we start to experience ohmic losses. Now you see here in this animation, we see that as the flux lines increase, the magnitude of the current flowing through the core, the ferromagnetic core, shown here in the black loops, it starts to increase. Now you see the flux lines are increasing and the currents through the core is also increasing, and the direction of the current through this core is such that it opposes the cause. So the cause is the external field, and the current flowing through this core will try to oppose the external magnetic field, and it is again given by the right hand thumb rule. So with that we can determine the direction in which the eddy current flows. Now, as we have discussed, that the ferromagnetic core has certain resistivity, so due to that we experience ohmic losses or the I square R losses, and these ohmic losses caused due to the current flowing through the ferromagnetic core is known as eddy current losses, and they can be determined as from the equation 2.18. Now comes the fundamental question that how to reduce these eddy current losses. Now to reduce the eddy current losses, we have to increase the electrical resistivity of the ferromagnetic core, and the resistivity of the ferromagnetic core can be increased by laminating the cores. Now this is again discussed in the book in detail, but we will try to see the impact of lamination through this animation. If we see here, the same ferromagnetic core which was used in the previous animation is now laminated, and we have 5 slabs, 1, 2, 3, 4, 5, and each of the 5 slabs is separated from each other by an insulating layer shown in the black color. Okay, so this black color represents an insulating layer. Now due to this insulating layer, each slab is electrically isolated from its neighboring slab. So there is an electrical isolation between all the 5 slabs. So the previously in the previous animation we saw one bulk material, but here instead of the bulk material we have laminated material. Now due to this laminated material, the nature of the eddy currents would change. Okay, so we can see here as the applied magnetic field increases, the eddy currents now follow a shorter path. They follow a shorter path because there is an insulation between the adjacent coils, and electrical insulation, so the currents cannot make a big path as they did in the previous animation. And as a result of this lamination, the resistivity of the ferromagnetic core, the electrical resistivity has increased, and this increased electrical resistivity actually results in decrease of the ohmic losses. My applied magnetic field remains constant, clear, but due to the increased resistivity we have lesser current flowing through the ferromagnetic material, and as a result of that we have lower ohmic losses or the I square losses. So lamination is one of the most important technique to reduce the eddy current losses in our ferromagnetic cores. And if you would have seen some machines or transformers, you would have seen that the cores are actually laminated, and each laminated section of the core is electrically isolated from its adjacent core by electrical insulation. So that insulation is essential to increase the resistivity of the ferromagnetic core. The details of those are explained inside the book on electrical machines. So we will not go into further details because of the time limitation that we have. So we have now seen the eddy current losses and the hysteresis losses, and both these losses together constitute the core losses in electrical machines. So with this, actually we come to the end of the theoretical aspect of the magnetic circuits. Now to understand the magnetic circuits in detail, we have some examples, and these examples are actually present in our tools. So here what we do is we choose some magnetic circuit. There are multiple problems available, but we choose the first one, and here we see that there is a ferromagnetic core, and around this core a coil is wrapped. Now what we can do is actually we can change the dimensions of this core. I can enter a value 310 millimeter instead of the default 300 millimeter value. So as soon as I do that, you would have seen that my core changed its dimension immediately. So I'll just go back to the previous value. I can change the depth of the core, so instead of 50 I can make it 55 millimeter, and if you see the core it gets wider. I can also change the number of turns in the core, and I can make it as 4, and now we have 4 coils. Now this is the 2D representation of the magnetic circuit. Now if I play 3D animation, it shows graphically that how this core is actually oriented. So this gives a better understanding of the magnetic circuit that we are going to analyze. And here in this animation we can see that how the flux lines they flow through this core. Okay, this actually helps a person to visualize and understand the magnetic circuit that we are about to analyze. So once we are satisfied with the parameter settings, we can press on freeze inputs, and then a new window appears where we have to enter some system inputs. So the first system input is the relative permeability. So maybe we set it to a value of 1000 and current through the coil. Let's say it's 10 amperes, and then we click on calculate. So as soon as we click on calculate, our first question appears, and this first question states that we have to find out the effective length of the ferromagnetic core. Okay, now we have studied the theory in the book, and applying that theory we will have to find out the answer to this first question. Let's say I type in 20 and I click on submit. So this answer happens to be a wrong answer. So upon clicking the hint, a very detailed 3D animation explaining the magnetic circuit in detail will appear, and by going through this animation, the learner or the student will be able to find the proper answer to this problem. So this animation is very detailed, and I must say that there are unique animations for each problem. So the animation does not remain the same, but it keeps changing for each of the questions. So every question has a unique animation associated with it. So after seeing this hint very carefully, we can find out that what would be the effective length of the ferromagnetic core, and actually the correct answer in this case would be 730 millimeter, and we click on submit, and it says congratulations, this was the correct answer. So we press on OK, and then the next button appears. So once we click on the next button, the next question appears, and it says calculate the effective length of the air gap. Now again here, if I enter certain value, this actually is the wrong answer, and if I click on the submit, again it shows the wrong answer and the hint button comes. Okay, now if I go through the hint very carefully, I would be able to find out what is the right answer to this problem. Okay, so the right answer to this problem can be found out using this expression over here, and if you see, the effective length of the air gap is equal to G, and G happens to be the gap which is 50 millimeter. So if I press here 50, it would be the correct answer, and it indeed is the correct answer. So we can see that the animations which are given here, they help the user to understand the problem, and then they also guide the user towards the right answer. So there are multiple problems available under this tools section, and there are problems for each of the chapter of the ebook. So these are really detailed problems which help the user or the learner to understand the theory that has been presented inside the book. Now besides the exercise, we also have quiz. So let's see the quiz. So first the teacher has to log in and has to set the quiz. Now if you see here, there are 8 chapters in the book, and there are questions related to each chapter. The chapter that we have discussed today is chapter number 2. So let's restrict our quiz to chapter number 2. So we see immediately the statistics of the questions available. So there are 40 easy questions, there are 12 questions with medium difficulty, and there are 30 questions with which are very difficult. So I'll set the quiz for today. Let's say there would be 4 questions, and the duration of the quiz would be easy. So duration of the quiz would be 5 minutes, I'm sorry, and the difficulty level would be easy. And we set 4 marks for the correct answer, and 1 mark for minus 1 mark for the wrong answer. So we save the quiz and then we start. So let's say I enter the student's name, which happens to be me, and I enter some roll number. I'm sorry, just I'll enter the roll number here, and submit it. And you see the quiz starts. So in the right pan, we see how much time is remaining and how many questions are there to be answered. So I click on the first question and then I go to next. For the second question, I want to skip the question because I'm not sure what is the correct answer, so I skip it. So here you see the real-time statistics of the question appears, and then I go to the next question and here to the next question, and with that I have actually finished my quiz. And here is the analysis. I attempted 3 questions and I passed 1 question. And out of the 3 questions that I have attempted, I got none of them correct. It was a very lousy performance that I had. So all the 3 questions that I attempted were wrong. I gave wrong answers and my total score is -3. Now this quiz has another unique feature because it allows the instructor to analyze the question paper of the students in detail. So here we log in and then we go to the analysis and then we click on the browse. So each answer script is actually saved, and this was the answer script which was saved just now. And here you see the complete details of my answer script appears. Now this helps the teacher to identify the topics which the student could not understand properly and help him through those topics. So it's a very helpful tool for the teachers as well, because they get a complete overview of the answers that the students gave. And this quiz is a part of the complete e-learning package on electrical machines. So this package on electrical machines is actually quite graphically intense. It's very interactive and it helps the learner to understand the subject in a very enjoyable fashion. So it is a very involved e-learning environment that has been created for electrical machines. So actually I would like to thank you all for attending today's webinar. I must say that this is the last webinar on electrical machines, and very soon we will be starting our series on power electronics. In case you want to have more information, then please do visit our website, which is www.deshya.co.in, and there you can drop in your comments and send us email for further queries, and we would be more than happy to answer you and help you. Once again, I would like to thank you all for attending today's webinar and have a pleasant evening. Thank you and goodbye.